There is a seductive illusion of control that sits right behind your steering wheel. It comes in the form of two plastic paddles, labeled plus and minus, or a separate gate on your gear selector. Manual mode. It promises the engagement of a sports car with the convenience of an automatic. Many drivers believe that by taking control of the gear shifts, they are driving faster, smarter, or more efficiently than the car's onboard computer. You might think you know better than the machine when to downshift for a pass, or hold a gear through a corner. But here is the uncomfortable truth that automotive engineers know, and you need to hear. In 95% of daily driving scenarios, your manual inputs are not just unnecessary. They are actively fighting against a system designed to be smarter, faster, and safer than any human reaction time. Modern automatic transmissions are not just hydraulic boxes anymore. They are supercomputers managing immense physical forces. When you intervene incorrectly with those paddle shifters, you aren't just changing gears. You are disrupting a finely tuned ballet of hydraulics, electronics, and physics. And the cost of this disruption isn't just inefficiency. It is premature wear, excessive heat, and potential catastrophic failure of components you probably didn't even know existed. Today on How It Really Works, we are going deep inside the brain of your transmission. We are going to expose the incredibly complex logic that dictates every single shift. We will look at 3 specific real-world scenarios where your manual intervention is causing hidden damage. And finally, we will tell you the exact, rare circumstances when you actually should take control. Put the car in drive, keep your hands off the paddles for a moment, and let's see how it really works. To understand why your manual inputs are often inferior to automatic mode, we need to move beyond the basic understanding of gears. Forget the old idea of an automatic transmission just being a slush box that guesses when to shift based on how hard you press the gas pedal. That technology is decades old. Today, the heart of the operation is the Transmission Control Unit, or TCU. This is the brain. And this brain is constantly eavesdropping on every other part of your car. It is not operating in isolation. Before a shift even happens, the TCU is processing a torrent of data from dozens of sensors across the vehicle. It knows things about the driving environment that you cannot possibly perceive. Let's break down the inputs that constitute the thinking process of an automatic transmission. First, there are the obvious ones: vehicle speed and engine RPM. The TCU constantly monitors the rotational speed of the input shaft coming from the engine and the output shaft going to the wheels. It calculates the precise ratio needed to maintain momentum without over-revving the engine or bogging it down. But that is just the surface level. The second critical input is throttle position and rate of change. It doesn't just measure how far down the pedal is pressed. It measures how fast you pressed it. A slow, steady press tells the TCU you want gradual acceleration, perhaps for fuel economy. A sudden, violent stab at the pedal triggers an entirely different algorithm, colloquially known as kick-down logic, preparing for maximum power output. Third, and this is where the computer vastly outperforms the human, is engine load calculation. The TCU relies on data from the mass airflow sensor and the manifold absolute pressure sensor in the engine. It knows exactly how hard the engine is working to maintain the current speed. Are you going uphill? Are you towing something? Is there a strong headwind? You might feel the car slowing down, but the TCU knows precisely why it's slowing down by analyzing engine load data in milliseconds. It knows if a downshift will provide more torque or just make more noise. Fourth, we have environmental sensors. Modern cars use inclinometers, the same technology in your smartphone that tells it which way is up. The transmission knows the exact gradient of the hill you are climbing or descending. It uses this data to prevent gear hunting, where an older transmission might endlessly shift between third and fourth gear on a long incline. The modern TCU recognizes the grade and commands the transmission to hold the lower gear steadily. It also monitors temperatures. Transmission fluid temperature is critical. If the fluid is cold, the shift points are delayed to help the engine warm up faster. If the fluid is too hot from aggressive driving, the TCU will alter shifting strategies to reduce friction and facilitate cooling, often by locking the torque converter earlier to stop fluid slushing, which generates heat. Some advanced systems even tie into the GPS data and radar cruise control. The car knows a sharp corner is coming up 500 meters ahead. It knows the speed limit just dropped. It can preemptively select the correct gear before you even lift your foot off the accelerator. So, how does it execute this decision? Once the TCU analyzes all these variables, speed, load, incline, temperature, driver intent, it consults a massive, multidimensional lookup table in its software. It finds the perfect intersection of all these data points and makes a decision. Shift from fifth to fourth. It sends an electrical signal to a bank of solenoids. These are electromagnetic switches inside the transmission valve body. The solenoids open and close tiny hydraulic channels. Highly pressurized transmission fluid rushes through these channels. This hydraulic pressure actuates pistons that compress specific clutch packs or engage brake bands. These clutches and bands lock and unlock different parts of planetary gear sets. By holding certain sun gears stationary while letting ring gears spin, the transmission creates different gear ratios instantaneously. And crucially, the TCU coordinates with the engine control unit, the ECU, to momentarily cut ignition timing or close the throttle for a fraction of a second during the shift. This is called torque reduction. It ensures the shift is butter smooth and, more importantly, that the clutches don't burn up trying to engage while full engine power is being applied. When you pull that paddle shifter, you are effectively shouting over this highly coordinated conversation between the TCU, ECU, and sensors. You are forcing a mechanical action without the benefit of all that sensory data. Let's look at the real-world consequences of doing this incorrectly. We need to examine 3 very common scenarios where drivers use manual mode, thinking they are helping, but are actually causing hidden stress. Scenario 1. The aggressive highway passing maneuver. You are cruising on the highway at 70 miles per hour in 8th gear. You want to pass a slow truck quickly. The instinct for a sporty driver is to grab the left paddle and click it twice, dropping to 6th gear before mashing the gas pedal. Here is what happens inside the transmission when you do that manually versus letting the automatic system handle it. When you manually force a double downshift at speed, you are forcing the transmission to disengage a high gear and engage a much lower gear while the driveline is spinning very fast. This requires the engine RPM to spike instantly to match the lower wheel speed. The synchronization effort on the clutch packs is immense. If you do this while already applying throttle, you are fighting the transmission's own safety protocols. The TCU has to scramble to manage the hydraulic pressure to prevent a jarring shift that could destabilize the car or slip the clutches, causing rapid wear. Contrast this with just pressing the accelerator quickly to the floor, activating the kickdown switch. The TCU sees the high rate of throttle demand. It instantly calculates the lowest possible safe gear based on current speed and engine load. It coordinates with the engine to rev match perfectly. It might jump straight from eighth to fourth in one seamless motion, much faster and smoother than your two manual clicks, and it does so with optimized hydraulic pressure that protects the clutch material. Your manual intervention was slower and rougher on the hardware. Scenario 2. The mild hill descent and engine braking. You are driving down a long, moderate grade. You feel the car picking up a bit too much speed. Instead of using the brakes, you decide to save your brake pads by downshifting manually to use engine braking. While engine braking is a valid technique in extreme situations, which we will cover later, using it for everyday mild hills is often a mistake in modern cars. When you force a downshift to raise RPMs and slow the car on a gentle slope, you are transferring the energy dissipation job from the brakes to the drivetrain. The braking force is created by the engine's vacuum fighting against the pistons, but that resistance is transmitted through the torque converter and the transmission gears. If the torque converter isn't fully locked up, you are churning the transmission fluid violently to create that resistance. This generates massive amounts of heat inside the transmission. Transmission fluid breaks down rapidly under high heat. Brake pads, on the other hand, are designed specifically to turn kinetic energy into heat and dissipate it into the air. They are cheap and easy to replace. An overheated transmission is neither cheap nor easy to fix. On a mild hill, it is far better to apply light brake pressure and let the TCU decide if it needs to downshift to assist. Don't force it to save $200 worth of brake pads by risking a $5,000 transmission. Scenario 3. The stop-and-go traffic crawl. This is a common habit in heavy congestion. The car keeps shifting annoyingly between first and second gear as you creep forward. To stop the jerking, you put it in manual mode and force it to stay in second gear, slipping the torque converter to move slowly. You feel smoother, but you are slowly cooking your transmission fluid. The torque converter is a fluid coupling. At low speeds in a higher gear, the impeller, connected to the engine, is spinning much faster than the turbine, connected to the wheels. The fluid inside is experiencing tremendous shear forces, generating significant heat. Normally, the TCU would shift to first gear to lock up the converter sooner or reduce this slip speed differential. By forcing second gear at crawling speeds, you are keeping the torque converter in its maximal heat generation phase for extended periods. This is silent damage that accumulates over time in urban commuters. So, is manual mode useless? Absolutely not. There are specific utility scenarios where your human foresight is better than the computer's reactive logic. Here is the utility guide: the 3 times you should use manual mode. Number 1. Severe, prolonged declines. We are talking mountain passes with steep grades lasting for miles. In this situation, relying solely on brakes can overheat them to the point of fade or failure. Here, you manually select a low gear, second or third, before you build up speed. You are preemptively setting up the car for sustained engine braking to manage safety, not just to avoid tapping the brake pedal on a small hill. Number 2. Towing heavy loads. When towing up a long grade, the transmission might constantly hunt between gears as the load varies slightly. It shifts up, loses momentum, shifts down, revs high, shifts up again. This hunting generates excess heat. Manually selecting a gear that keeps the engine in its power band and holding it there provides a steady pull and protects the transmission from constant shifting stress. Number 3. Low traction surfaces. If you are trying to start moving on ice, snow, or deep mud, first gear might provide too much torque, causing the wheels to spin instantly. Many cars allow you to manually select second gear for a stationary start. This reduces the torque reaching the wheels, helping you gain traction without spinning out. To conclude, the golden rule of modern automatic transmissions is this: respect the complexity of the machine. The engineering team that designed the shift logic spent thousands of hours calibrating it for efficiency, performance, and longevity. Unless you are in one of those extreme utility scenarios we just mentioned, the D position is almost always making a better decision than you can with the paddles. Enjoy the drive, but let the computer do the thinking. It's what it was built for.